All right, guys, welcome to section 3.5. We are going to be examining implicit differentiation. All right, so implicit differentiation. So let's talk about that word, implicit. So up until this point, we've been dealing with explicit differentiation. So explicit, it's kind of clearly defined when we're talking about explicit. We're being very direct. And in this case, what we're talking about is we're being very direct and very clear on what y is equal to, the dependent variable. So we've been doing differentiation to things like, y equals 4x squared minus the square root of tangent of 3x plus 10 to the x, all right? These are all crazy things. We could actually take that derivative now. We have a lot of tools in our toolbox right now. Now we're going to add another one because now we're going to be talking about implicit differentiation. So implicit is kind of not as direct, right? Kind of implied, implicit differentiation, and we're talking about the y. So now y isn't clearly as defined as explicit. So in this case, what we're going to see is that y is going to be tangled up in the equation. And we're not going to be able to solve for y. It's going to be mushed up with the x's. It could be part of a radicand that also is in terms of x's. And no matter how hard we try, we're not going to be able to get y by itself. So we still have to be able to take the derivative of something that looks like that. And we're going to do it by something called implicit differentiation. See, this definitely looks crazy, right? And you could think, why are we ever going to use this? We've never seen anything like this before. But something that doesn't look as crazy that we've definitely seen before in our algebra class is like a hyperbola. Hyperbola and other parabolic graphs are, implicitly defined. X squared minus y squared is equal to 9. There's no one equation that we could solve for y. At best, we would need two equations, right? So this is definitely a skill because we can definitely look at a hyperbolic curve and we could ask the question, what's the slope of this tangent line? That's a definite, possibility. We can visually see that that's something that we could need. So we would need to find the derivative of x squared minus y squared is equal to 9. We need to be able to find the slope of that tangent line. So here's how we're going to approach it. So to do our implicit differentiation, to take the derivative with respect to x, all right, and in general, that just means the independent variable. So y is the dependent variable. We're going to take the derivative with respect to x of both sides. That's that notation, d dx of both sides. And we're going to solve for y prime. That would give us the derivative of those implicit equations. All right, and I say y prime, but it could also look like dy dx because y prime is dy dx. Okay, so we're going to need our chain rule. And I'll show you why. So this involves the chain rule. Okay, so remember we're assuming that x is the independent variable and y is the dependent variable. So we're assuming that y is in terms of x, is a function of x, or it's not a function, but y is in terms of x. Okay, so we're going to eventually take the derivative of y with respect to x. Okay, so what's this going to look like? Let's look at an example of a circle. And we'll call this circle x squared. We'll have it centered around the origin, and the radius is 3. So that means x squared plus y squared equals 9. Okay, and we're going to want to find the derivative. And we're going to do this by implicit differentiation, because notice we have our y's mixed in with our x's, okay? And there's no one equation for y that would give us a circle. We can do it in 2 equations, but we can't do it in 1 equation. So that's why we're going to do implicit differentiation. There's no one explicit equation for y. So our instructions were to come and take the derivative with respect to x of both sides. This is implicit differentiation. Okay. So then we know that we're allowed to, over here on the left, kind of distribute that derivative with respect to x to both sides. All right, so let's start taking the derivative. So there's a couple of these that we already know how to do. All right, for instance, the derivative of x squared with respect to x is just 2x. That's our power rule. We also know that the derivative with respect to x of a constant is 0. Okay, and so what are we going to do about the derivative of y squared with respect to x? Well, I just said that y is in terms of x. Okay, so y is a function of x. So sometimes what's a little bit helpful, I'll do a little thought bubble, is think of y in terms of, y to the x. Y is a function of x. So if we're looking at y squared, like we have here, well, that's going to be our function y of x squared. So this is where our chain rule comes in, because we're going to have to take the derivative. We have an inside function, that's our y to the x, but now we have our outside function squared. So we're going to take the derivative of the outside function, so bring that 2 down, and then we have to take the derivative of our inside function, y. All right, and then this only happens with that implicit differentiation. So again, for the derivative of y squared with respect to x, take the derivative of the outside function first, and then inside function stays the same. Then you multiply it by the derivative of the inside function. So dy dx, or you can write y prime, something like that. Okay, so we had to use the chain rule right here, because y is really a function of x. So we have the outside function that's squaring the y, and our inside function is y. Okay, so next, after we do our implicit differentiation, we have to solve for y prime, or dy dx. Okay, so sometimes it helps, because sometimes there's a lot of dy dx's. Sometimes it helps to highlight them. And normally when we solve for a variable, every term with a variable stays on one side, and everything else goes to the other side. So all the dy dx's will be on the left, and if a term doesn't have a dy dx, it goes to the right. Okay, so in this case, since we're solving for dy dx, let's subtract 2x. So we have 2y times y prime, or dy dx, is equal to negative 2x. Okay, and again, it's still helpful to highlight, because remember, once all the terms are on one side, and you simplify and get it down to one term, you divide out by the coefficient. And in this case, the coefficient is 2y. So we're going to divide both sides by 2y. Okay, and then we're almost there. What are we left with? We're left with dy dx is equal to, let's see, negative 2 over 2 is 1, or negative 1 rather, and we're left with negative x over y. So there you go. Negative x over y is our our derivative function of a circle. Let's see how this works, because this is still a little bit crazy, because normally when we have a derivative function, we just have it in terms of x's, but there's some definite y's in there. So let's see how that plays out. So we're going to do an example using the same x squared plus y squared equals to 9. And now let's find the equation of a tangent line. Let's find the equation of the tangent line at root 5, comma 2. Okay. And it's the same problem. So if we go up here, root 5, here we go, root 5 and 2. So notice that it fulfills our equation. Root 5 squared is 5, plus 2 squared plus 4. 5 plus 4 is 9, okay? So it's definitely on our circle. Maybe it's somewhere like right here. Okay, so there's your root 5, and maybe there's your 2, approximately, right? And now the equation, or the problem says we're going to find the tangent line. So we're going to find this tangent line right here, the equation of that tangent line. To find the equation of a tangent line, we need a slope and we need a point. Well, we have a point. The point is root 5, 2. So the only thing we need is the slope. How do we find the slope of the tangent line? That's the derivative. Okay, so we have a point. It's root 5, comma 2. The slope of a tangent line, remember, is the derivative. And we know that the derivative is negative x over y. That's what we just found right here. Negative x over y. That's what we just did. So let's see. Well, we have x and y. X is root 5. And y is 2. So the slope is negative root 5 over 2. Okay, so we have everything we need. I'll write out the equation of point slope form. Y is 2. M is root 5 over 2. And x is root 5. Okay, so that's us plugging in the points. Let's clean it up a little bit. I'm going to distribute the root 5 over 2. And then when I distribute it to the root 5 times root 5 is just 5. And now we can add 2. Okay, and when we add 2 over yonder, we need the same denominator. So 2 is the same as 4 over 2, right? 4 divided by 2 is 2. So I'm just going to do this all in one step. And then that's going to be, I made a mistake. Should I go back and fix it? Did anyone catch my mistake? What did I forget on the slope? The minus sign. So how's that going to change things? Not by much. It'll change that, and minus minus becomes plus. All right, so easy fix. 5 plus 4 is 9. And right there, of course. All right. And that's our equation of the tangent line. So implicit differentiation, our derivative was in terms of x's and y's, but in the end it was okay because our points, like when we create these tangent lines, it's in terms of x's and y's as well. Okay, let's look at an example, and we'll do one more example together, and then you guys can try an example on your own. Okay. We're going to find the derivative of the following. X cubed minus 2y cubed plus 2xy plus y squared equals 0. All right. And then what are some, if we want to find the derivative, what are some ways we can tell that we're going to have to use implicit differentiation? All the y's are all muddled with the x's. Okay, so we have a strategy for implicit differentiation. We take the derivative with respect to x of both sides. Okay, and then of course after we distribute, that's like taking the derivative with respect to x of each term. So let's write that out. So we're going to be taking the derivative with respect to x of x cubed minus the derivative with respect to x of 2y cubed plus the derivative with respect to x of 2xy plus the derivative with respect to x of y squared equals the derivative with respect to x of 0. Okay, so let's hop to it. So there's a couple of these, actually just two, is our old school derivatives, right? So when it's just in terms of x's, that's old school, right? That's just going to be 3x squared. And likewise over yonder, that's just the derivative of a constant. Derivative of a constant is 0. But everything else is our new stuff. We have to use our implicit differentiation and the chain rule, sometimes even more than that. So let's hop to it. This is going to be a longer problem. So the derivative here is 3x squared. All right, we should be feeling really comfortable with that. And then minus the derivative of 2y cubed. So remember, y is a function of x. So we have an inside function 3, and then our, outside function is a cubic function, then our inside function is y. So we're going to be doing, let's see, we have our constant. We can deal with the constant at the end. We're looking at 3y squared, that's the derivative of the outside function, times the derivative of the inside function. And if you don't mind, I like to just write y prime, but you can definitely write dy dx. Okay, good. Plus, and now we have 2, or we can kind of deal with the constant at the end, 2 times xy. So here, this is a product. X times y is a product. So we have to use our product rule. Okay, we're going to use our product rule. So we'll do first function and second function. So let's do x and y. So we'll do first function, x, times the derivative of the second. And remember, y is a function of x, so that's y prime. right? Because we're taking the derivative with respect to x. And then we're going to add y times the derivative of x. All right? And the derivative of x with respect to x is just 1. Okay. So there's that. Let's keep going. So now we have the derivative of y squared with respect to x. So again, we're assuming that y is a function of x. So outside function first. So bring down the 2. And then inside function stays the same. And then we take the derivative of the inside function. Okay, we're almost done. What's the derivative of 0? 0. All right. So now is the time to clean up everything. So let's go through and clean up all our terms. Okay, second term, let's see. We can do a 2 times 3 is 6, y squared, and then we have our y prime or dy dx. Here, let's distribute our 2. So we have a 2x y prime plus 2y. And then we have plus 2y y prime equals 0. Okay, and I think that's as far as the simplifying goes on the left. So now our goal with implicit differentiation, once we take the derivative with respect to x of all the terms, it's time to solve for y prime. So we're going to identify, and again, I like to highlight, we're going to identify all the y prime terms. And there's 1, 2, 3 terms with y prime. So all these terms, 1, 2, 3, are going to stay on the left. And that means we're going to send 3x squared over to the right. So subtract 3x squared. Okay, that'll take care of that. Let's subtract 2y to get it out of the left. And whatever we do to one side, we got to do to the other side. Okay, so that's how we solve for terms. We gather them all on one side. Okay, and again, feel free to highlight all your y prime, because that's what we're solving for. So it's just helpful to really see it pop. And now that we have all of these terms on the left with y prime, we're going to factor out that y prime. So remember, factoring is like going through and dividing each term by y prime. And we're going to factor it out. And we're left with 6y squared plus 2x plus 2y. And it equals this. Okay, and again, feel free to highlight. And we're almost done. So we have y prime times this thing, kind of like coefficient, is equal to that right-hand side. So your final step when solving is you divide out by the coefficient. Whatever you do to one side, you do the other. Okay, and we're there. We have an equation for y prime or dy dx. Not really, doesn't really matter which one you use. The only thing that's nice about dy dx is we know that we're taking the derivative with respect to x. Okay, so that's one advantage of using that one. I like using y prime in this case because it just gets so busy. And for me, y prime is a little cleaner. Okay, so there you go. I mean, you could leave it like that. There's definitely some simplifying that we could do if we wanted to do it. For instance, we can factor out a negative in the top and bottom. Factoring out negatives, remember that just changes the sign of everything on the inside. That's one thing if we really wanted to simplify it. Okay. And then it's nice because minus minus, it's like -1 over -1. That's just going to cancel. Or minus minus becomes plus. Okay, so that's an option. It looks a little bit nicer. But it's not completely necessary. All right, so either answer is okay by me. Okay, so let's look at another example. You guys are going to do this on your own, so let me write it out, and then you guys can push pause. Work out the example, and then we'll go over our solutions together. So find dy dx of the following. All right, so push pause. Okay, welcome back. So definitely we see the x and y's are muddled together. We can't get a formula for y all by itself. So we're going to take the derivative of both sides with respect to x, okay? And after we distribute, it's like taking the derivative with respect to x of all terms. All right, and remember, we're taking the derivative with respect to x. So x is the independent variable. So if it's just in terms of x's, it's like how we do our explicit differentiation. This is just going to be, like bring down the exponent and then that's that. But here we have a y. So we have to assume that y is a function of x. So we're going to have to use the chain rule wherever we see a y. Okay, so again, this is old school. So you bring down the 2. 2 times 2 is 4 times x to the first. Okay, and then we have a chain rule here. X times y is the chain rule. We want to take the derivative. So let's see, we can do first function times the derivative of the second plus the second function times the derivative of the first. Derivative of x, again, that's just in terms of x. So derivative of x with respect to x is 1. All right, and then second derivative y squared, y we have to assume is a function of x. So we have to take the derivative of our outside function first times the derivative of our inside function. And then what's the derivative of a constant? 0. All right, we can clean this up a little bit. It's not too crazy though. All right, so once we take the derivative with respect to x of all the terms, then we have to identify all the y primes, all the terms with a y prime. Okay, so we're going to bring 4x, y, and -2y to the right, and we're going to keep these two terms, xy prime, and then -2y, y prime. All right, so you guys, subtracted 4x, subtracted y, you added the 2y. Whenever you do to one side, you do the other. Minus. Okay, so what did you get? You have xy prime minus 2y, y prime equals oh my goodness. I made a mistake. Did you catch it? Got it. Right there. Sorry about that, guys. That's all one term. We all make mistakes. We always feel good when we catch them. All right, so nothing a little eraser can't handle. So where are we at? Y prime, y prime. Let's factor that out. And then last step is we divide out by that coefficient. Again, you can keep it highlighted to help. And then we're at our y prime. And you can write y prime again, you can write dy dx. I'm fine with either. And we have the negative 4x minus y over x minus 2y. And I'm fine with that format. If you wanted to factor out a negative and bring it out to the front, that's fine too. Okay, so we can write our solutions in different ways. All right, so there you go. So we're going to do a couple more things. We're going to talk about the double derivative, double derivatives, and then we're going to be talking about the derivatives of inverse trig functions. But we're going to do that in part 2 of our video.